So now that we've talked about solubility equilibria, we've done some calculations, I'm going to talk about the common ion effect. Now this is something that we're talking about with respect to solubility, which is normally where you encounter this topic, common ion effect, but it's actually related to other topics, including buffers. So, we learn about buffers, and if you have an aqueous acid, a pure acid, and we're just dissolving it in water, then you're going to form some hydrogen ion on the right-hand side. But if you already have some of the conjugate base present, like you do in a buffer, then that's going to resist formation of the hydrogen ion. That equilibrium doesn't lie as far to the right because you have some of that ion present already. So that's an example of common ion effect, and your book presents it in that order. It's an early topic in your book, but we're going to talk about it more with respect to solubility. So the solubility of salt is decreased by the presence of a common ion. So that would be an ion involved in the solubility equilibrium. So if we use our original solubility equilibrium that we used when we first introduced solubility, calcium fluoride, dissociating into calcium ions and 2 fluoride ions, then the common ions in this case would be calcium or fluoride. The presence of either one of these in the solution already would shift this equilibrium to the left. That's what Le Chatelier would say, right? Le Chatelier's principle says that if we add products, the equilibrium will shift to the left, which is the solid side, which is going to decrease the solubility of the salt. So now this is a picture from your book which shows the solubility of magnesium fluoride in moles per liter along the y-axis as a function of concentration of sodium fluoride. So we're trying to dissolve magnesium fluoride. If we're trying to dissolve it in water, that would be along the 0 point, and you can see that that's the pure water, that's the highest solubility. And then it decreases pretty rapidly as we increase the concentration of, in this case, it would be fluoride ion. The sodium ion does not influence the solubility because it's not a common ion, but the fluoride does influence the solubility because it's part of the magnesium fluoride solubility equilibrium. Now in our saturated solution that we had previously, calcium fluoride, when we had it here. So if this is our saturated solution, I made it bigger, right? Now it's this big giant font, and I made it big because the concentration itself is a larger number. So what that means is because calcium times fluoride squared, that's a product, that is a constant at the same temperature. So we haven't changed the temperature, which means that if we've increased our calcium concentration, the fluoride concentration even more, right? Because they combine to be KSP. So if they're always equal to the same constant, when one of them goes up, the other one has to go down. And so what that means is that the calcium fluoride will precipitate. The reaction will proceed to the left, and we'll get some calcium and fluoride coming out of solution and combining with the solid. So now we have a different equilibrium that's established that has different concentrations, but the value for KSP is the same. So if you take the calcium concentration and the fluoride concentration above the solid, whatever is in the aqueous phase, if you plug those into KSP, you'll still get the same KSP. So this picture is a similar idea. It's just that when you add calcium or fluoride, that shifts this solubility equilibrium to the left. So we're going to talk about the various factors that influence solubility equilibria. One of them is the common ion effect, which we have also already defined. Presence of an ion that is common to the solubility equilibrium will decrease the solubility of that salt. pH also influences the solubility if the salt is acidic or basic. And the formation of complex ions will also influence the solubility of the salt. So here we're going to calculate the solubility of barium carbonate in a 0.1 molar barium nitrate solution at 25 degrees. So you're going to set the problem up the same way you did before when it was in pure water. But instead of being in pure water, we have 0.1 molar barium, which means that in our ice table, we're going to fill in a number for the initial concentration of barium. I'm going to plug in 0.10 and then 0 molar carbonate, and then plus X and plus X, and then 0.10 plus X and X. For the carbonate concentration, we're going to plug those into KSP. And then we're going to solve for X. You can assume that X is negligibly small compared to 0.10, or you can use the quadratic equation. Either way, you should get the same value, 2.6 times 10 to the minus 8. And then we're going to multiply by the molecular weight to get the concentration in grams per liter. This is certainly lower than it was before. And so the presence of barium ion does decrease the solubility. This is way lower than it was in pure water. I think it was times 10 to the minus 2, 4 orders of magnitude lower now. So way lower in the presence of a common ion. It was 1 times 10 to the minus 2 grams per liter. Now pH. Basic salts are more soluble in acidic solution. So the solubility of calcium carbonate increases as the pH decreases. The reason for this is because calcium carbonate is a basic salt. It is the conjugate base of bicarbonate, which is a weak acid. And so as the pH goes down, that means that there's hydrogen ions in the solution. The solubility of any basic salt will increase as pH decreases. And the reason for that is because we have calcium carbonate. We're trying to dissolve it in water. This is the salt that's shown in the graph. If we add hydrogen ion is going to interact with the carbonate and it's going to form bicarbonate. So any basic salt is going to combine with H+. The H+ will react with the base and it will form the conjugate acid. But what this means for the solubility equilibrium is that we've removed carbonate from the solution. So this carbonate reacts, decreases the concentration of carbonate. Back when we were learning Le Chatelier's principle, all I would say is that we've removed carbonate. But the decrease in carbonate will shift the solubility equilibrium to the right. So because the hydrogen ion reacts with it, that removes it from the solution, shifts it to the right based on what Le Chatelier would have said. Product removal shifts the equilibrium to the right, as it always does.